All right, in 3.2a, we're looking at polynomials and specifically finding the zeros or x-intercepts and what's called the multiplicity of each. All right, so polynomials functions are continuous functions with smooth rounded terms. Okay, they have curves. Okay, not like absolute value, not v's, but curves. Now, we say that because we are looking at what's called the leading coefficient test, and this is going to tell us the end behavior of the ends of our polynomial, like which way are they pointing, up or down, basically. So what you're going to do is look at a polynomial. It could be forever long, doesn't matter, but you look for the highest exponent of x, and you're looking at that coefficient that goes with it. That's the leading coefficient. Okay? You have to find the highest exponent of x and its coefficient. Now, what you need to do is if that exponent is odd, okay, and a, the coefficient, is greater than 1, okay, meaning it's positive if it's greater than 1, then it's going to mimic the easiest parent function we know with an odd power of x, which is a linear function, okay? So if it's positive, if that a value is positive, it's going to go like this. And here's what I mean by end behavior. What I mean is that it falls left and it rises right. Okay? That's what I mean by end behavior. Now, if it's odd, but that a is negative, then think of it like the negative slope of a line. And to describe its end behavior, it rises left and it falls right. Okay, easy enough. Now, when that exponent, the highest exponent, is even, it's going to mimic the easiest even exponent we know. Parent function is x squared. Well, that's like a parabola, right? So if that a value, that coefficient, is positive, then it's going to be like a parabola that goes up. And you would say it rises left and it rises right. And then, I bet you can figure this out, if it's negative, then that would flip our parabola upside down, and we would say it falls left and it falls right. Now, it's not going to be a perfect parabola because it could be like x to the 6th power. It doesn't matter. The ends will go in the same direction if it's even, and the ends will go in opposite direction if that power is odd. Right? Now let's try some of these. So I want to describe the end behavior of the polynomial function. So first of all, I look at my problem, and I look at where's the highest exponent, which is x to the 3rd, and its coefficient. Okay, so the exponent is odd, and look at that a value. It's -1, so it's negative. So odd means it's going to work like a linear with a negative slope. So I would say it rises left and it falls right. Okay. Look at number 2. Odd and positive. Okay. So think your positive linear line. What does that do? This one will fall left and it rises right. Okay. Look at number 3. It's even and it's positive. Okay, so think of your parabola, positive parabola, and you would say it rises left and it rises right. That's all you have to say. All right, example 4. Even and negative. So what would that do? It's like a parabola upside down. So we could say it falls left and it falls right. Now, just word to the wise, sometimes these equations can be out of order. They don't have them in exponent order. So you may need to look real carefully about where is the highest exponent. It may not be the first number listed. So just keep an eye out on that, but it's going to follow these patterns each time. Now, repeated zeros yields a repeated zero, okay? A repeated factor like this, okay? It's like, for instance, an x plus 3 factor. If you're factoring something and you see a lot of x plus 3s, well, if you saw that, that's x equals 3, right? It just may mean that you have a double root, a triple root of anything like that. Now, we call that multiplicity. Multiplicity. K is how many times does it appear? Is it single, double, triple, on and on and on. Now, this value of k helps us know how does that line cross the x-axis, okay? If k is odd, meaning that factor shows up one time, it just passes through the x-axis, crosses like normal. If that k value is even, like a double root, that means that the graph is going to touch that x-axis and bounce off of it. Okay? I often call it a bounce more than a touch. But it will touch it. It could touch it from beneath, it could touch it from above, but it just touches it and goes in the opposite direction. So what you're going to do is find the zeros and determine the multiplicity of each zero. So what does that mean? It means factor it first, guys. So this guy, if I factor it, this is x plus 5, x minus 5. Now if I look at these individual factors, there's only one of this kind and there's one of this kind. So my 0 would be x equals negative 5, and it has a multiplicity of 1. For this root, if I solve that, I get x is equal to positive 5. It also has a multiplicity of 1 because it only appears one time. This factor appears one time. On example 6, what should I do? Let's see, I should factor out a t first, and that gives me t squared minus 4t plus 4. I can keep factoring. I'll have t minus 2 times t minus 2, which is t times t minus 2 squared. So if I set these equal to 0, I have t equals 0, and I set this factor equal to 0. That gives me a t value of 2. So there's my two zeros, or roots. This t right here has a multiplicity of 1. It's t to the first power out here. But this guy, it appeared twice, right? We wrote as squared. So this one has a multiplicity of 2, which means that if I were graphing this, it would bounce where x is 2. All right, let's try a few more of these. Let's start by factoring. I want to get my highest exponent with a positive in the front. So I'm going to factor out a negative 2x squared out of this guy. That'll give me 2x squared minus 1, okay, equals 0. And then I can set each part of that equal to 0. Well, this will solve. If I divide by negative 2, it's still 0. X squared is 0. That means x is 0. But since it was x squared, it has a multiplicity of 2. Right? So there's one of my zeros and its multiplicity. Here, if I move the 1 over, I get x squared equals 1/2. If I square root all this, I'm going to get x is plus or minus 1 over the square root of 2. So that's really 2 roots there. So x can equal a positive 1 over the square root of 2, and x can equal a negative 1 over the square root of 2. Okay? So this has a multiplicity of 1, and this one has a multiplicity of 1. All right? So that works just fine. There's 3 roots. This one has a multiplicity of 2, so that's where the 4 comes in right here. It should add up to 4. There's 1, 2, 3, 4 roots. All right, so let's look at number 8. Again, I would start here by factoring an x out. So I have x squared minus x minus 2. Then I can factor this. This will be x minus 2 times x plus 1, and I'll bring that x straight down. It's all equal to 0. So then I have a 0 at x equals 2. I'm sorry, x equals 0, x equals 2, and x equals -1. All right, notice how the signs change when you solve it, Chris. Just FYI. Now, each of these factors at this step had a power of 1 on them. None of them got repeated, so each of them has a multiplicity of 1. All right, so there you have it, finding the zeros and their multiplicities. All right, look at this last number 9. And again, we would start by factoring an x out of each term. X squared plus x minus 6 equals 0. If I keep on factoring, I'll get x plus 3 times x minus 2. If I set each of these equal to 0, I'll have x equals 0, x plus 3 equals 0, and x minus 2 equals 0. If I solve these, I have x equals 0, x equals -3, and x equals 2. Now, look at the factored step right here. They're all to the power of 1, so they all have a multiplicity of 1. All right, there you go. So today you're going to be finding zeros and their multiplicity, as well as finding in behavior. All right, we'll see you in class.